Hi and welcome to this new video. We continue with the transient response of second order circuits. That is our example number 1. We will consider the RLC series circuit. In this example, we have a voltage source VM, there's a switch that will be closed at time equals 0, and there are 3 components R, L and C. The values of the components are shown here on the right, and the voltage source has a voltage level of 1 volts. Okay, so what's the question in this case? The question is determine the capacitor voltage VC for time larger than 0, and we assume there is no energy stored in the inductor or the capacitor when the switch closes. So we assume that such that the initial conditions are clear for the analysis. Okay, now as we did also for the first order circuits for the transient response analysis, we will follow a specific procedure step by step. But for the second order system, we have some additional step to take, so that will be clear also during the analysis. What we want to do and what we like to determine is the capacitor voltage. So I will underscore this, so capacitor voltage. So what we need to write first is what's actually the capacitor voltages for the second order systems. Now, the capacitor voltage VC is actually the force response of the capacitor voltage. I will denote it by the F subscript, plus the natural response of the capacitor voltage. And this will be as a function of time, and the force response will not be a function of time, as we will see shortly in this case. So this will be I will make this clear, this will be the forced response. So this part, that's the forced response. And this part will be, I will make it in blue, this will be the natural response. Now the first forced response, the red one, will be determined by the applied voltage by the independent sources. So in this case, this is the VM. The natural response will be determined by the components themselves, and also, of course, the other independent voltage sources and current sources. So this will be determined by the components which are actually by itself present in the circuit. So that's actually why it's called natural response. Okay. The next step is how do we determine the force response and how do we determine the natural response. So if you know both of them, you can add them and we know the answer. Okay, the force response. Let's start. Let's start with the situation for the initial value. So what is the initial value? The step 1. Initial conditions. Okay, so initial conditions, what are they? As we can see from the circuit, since the switch is open, there is no current flowing through the resistor, inductor and the capacitor, so the current IL and also the IC for the capacitor will be 0. And the voltage across the capacitor will be also 0 because there is no current flowing and there is actually no connection to the voltage source VM. So we can already say for this case the IL at 0, which is the initial value of the inductor current, will be 0. But the V capacitor at 0, the initial value of the capacitor voltage, will be also 0. So these are the two values we have determined for the step 1. What we also need to determine, which is not done in the first order systems, first order circuit analysis, is the situation for at switching. So just at the switching, we will denote this by at time equal to 0 plus. That means just after the switching, what happens? Now the situation is like this. We have the circuit. I will draw it again to make the situation more clear. So we have the connection made. So there is the R, there is the inductor, and there is the capacitor. So the situation is like this. And what we like to know is what is the value of the capacitor just after the switching. and also that might be also required. It is useful to calculate it also, even if it is not required here in the question. What is also the inductor current at switching? Now, for the inductor and for the capacitor, there is a condition for the continuity. So continuity condition says that the capacitor voltage cannot change instantaneously, and the inductor current cannot change instantaneously. So there is required finite time for that. So what this implies is, in formula form, the capacitor voltage at 0 plus is equal to the capacitor voltage at 0. That means it will not change just after switching. This will also hold for the current for the inductor. So the IL at 0 plus will be the IL at 0, and it's also at this time 0 volts, or 0 amps, and that's also 0 volts for the capacitor voltage. This condition, I will make this clear, we require this in the final solution of the capacitor voltage as a function of time. In addition, for the total response, this is total response, we require also the initial value of the derivative of the capacitor voltage. So this is the one of the initial values, and we need also another initial value. So I will make this clear here. So what we require is the situation for the initial value for the capacitor voltage, but we also need the derivative of the capacitor voltage evaluated at time equals 0. So these two are required to calculate the response of the capacitor voltage. So I will move on to this derivative. So where is the derivative actually hidden in the capacitor expressions or the formulas for the capacitor voltage and the capacitor current? Okay, so we know that the capacitor current, IC, in general, is equal to the capacitor value C times the derivative of the capacitor voltage. That's the formula we should know from circuits basics. So what we have is actually the derivative of the capacitor voltage is actually IC, the current of the capacitor, divided by the capacitor value. So if I rewrite this, I will have this, and which is actually the required expression for one of the initial conditions. So if I now evaluate this at 0, because evaluating it at 0 or evaluating it at 0 plus, that doesn't matter because due to continuity, so I can say, the following. So the capacitor voltage at 0 plus is equal to the capacitor voltage at 0. So the capacitor voltage at 0 plus, derivative of that is equal to the current of the capacitor at 0 plus divided by the capacitor value C. But the thing is, what is actually the capacitor voltage at 0 plus? Now actually that is also equal to the inductor current, because that will not change instantaneously. So what we will have here is the following. The IC at 0 plus will be IL at 0 plus, and that will be also 0 ampere. So I can fill in the formula which is required for our calculation. It is actually 0 divided by the value of the capacitor. That doesn't matter what it is at the moment. So it will be also 0, and it will be 0 units volt per second. And I will also make this clear. This is also one of the required values for our final result. So I will make this clear by denoting this is 1 and this is 2, condition 2. Alright, so this is actually the situation for just at switching. Now what we'd like to know is also the situation for the final or the steady state condition, and the final condition calculation will give us the forced response. So that's actually step 2. So let's move on. And for step 2, what we know is the switch is closed, and because of this final condition situation, the inductor will behave as a short circuit. That is actually the model we have used also for the first order analysis. and the capacitor will behave as an open circuit, so we will also use that. So I will emphasize it also. So step 2 will be the final value, final condition, final value, and this will be for the force response. So we will determine the force response from this analysis. Okay, so I will redraw the circuit again. So we have the voltage source present, that is the VM, and the resistor is in place. The inductor is modeled by a short circuit, but the capacitor will be an open. So if I place the values or denote the capacitor voltage and the inductor current by the sign infinity means the final value, what do I have? Now if you see clearly the IL at infinity will be 0 because there's no current flowing, there's an open circuit, but the capacitor voltage final value will be Vm, and that is actually equal to 1 volt. So I already said the force response will give us the final value will give us the force response. So this is actually the capacitor voltage force response. So I can say this is also the force response. So this is actually one of the unknowns for the expression of the capacitor voltage. We already determined this. That is actually number one of the unknowns in this expression. So this one, the natural response, is actually our next step, the step 3. So let's start with that. Now during step 3 and actually during natural response analysis, what we are interested in is actually the situation when the components are present and there are no independent voltage source or current source, or all of them are disabled. So I will do that. I will keep the circuit as it is, but I will disable all of the independent voltage sources or the current sources. But in this time we have only the VM, so that will be a short, as we know. So what we have is, I will zoom out a little bit and I come here to make some room. So what we have is the step 3, that will be the natural response. Okay, so natural response, let's redraw the circuit again. So we can see the situation more clearly. So of course there is a short, I forgot that. Okay, that's a short, that's an R, that's still present. The inductor is still present here, and the capacitor. So we have the capacitor, we have the inductor. What do we have? Now situation here is just for the natural response, so I will again denote the current and the voltages we require. What we can say here is actually the following: the current through the inductor is exactly the same as the current through the capacitor, and the voltage actually here is, using the Kirchhoff current law, is the voltage across the resistor plus the voltage across the inductor plus the voltage across the capacitor will be 0. So I can already say that. So let's write down two situations we have discussed. So the Kirchhoff current law will give me that the IL is equal to IC. This is actually the situation here, and I know that the Kirchhoff voltage law will give me the IC times R, that's actually the voltage across the resistor, plus the VL, that's the inductor voltage, plus the capacitor voltage VC is equal to 0. Okay, now in this situation I would like to have an expression using these two formulas, a second order differential equation I will get, but just I would like to see the V capacitor. So the capacitor voltage in the expression, and there are other elements or other unknowns, I would like to replace them by the capacitor voltage. So what can I do? I will need to replace this, and I will need to replace this. So we know some of the formulas that can help us, so I will write it down here. So the capacitor current, we already seen this, is equal to C times the derivative of the capacitor voltage divided by the derivative of the capacitor voltage. But the inductor voltage is the L times the derivative of the inductor current. So we can use this also here. And since we know that the inductor current here is equal to the capacitor current, this will be actually give us a second order term, or the second derivative. So I will write it down step by step. So what we have is actually the following. This one will be, the first term will be R times C times the derivative of the capacitor voltage. The second one will be the L times the derivative of the inductor current. Of course, that's also the capacitor current, but I will replace that shortly. I just want to go step by step so that you can follow it. And the VC, I would like to keep it as it is because I'm interested in that parameter. So what we like to do now is replace the IL by IC because it is equal to each other, and I will use this formula again to replace this, and I will move this to the left, and I will make this such that the second derivative comes first and the first derivative comes after that, and then the zeroth derivative comes in the third place. So what I have is, if you place it here, I will get the L and the derivative of that, and then the C, this is just the IC fill we have here, and then R times the C and the derivative of the capacitor voltage, and then plus the capacitor voltage, which is equal to 0. Now what I do now is I will simplify this, so I can divide by L and C, left and right, and I will simplify this such that the second derivative is also given in the expression. So I will have the following. I will have the second derivative of the capacitor voltage plus, because I divide by L times C, I will get R divided by L, and I will get here 1 over LC times the capacitor voltage. Now what I now use for in this situation, I will set the following. I will set where I see a derivative of the capacitor voltage, the first derivative, I will set that equal to S. So I will define a variable S. This is actually also the Laplace parameter. We have you might seen this before in other courses. So what we'd like to do now is just rewrite this using the parameter S. So we will have an S squared, and R divided by L times S, and 1 over all C. So this will be 1 if you use the operator, and this will be 0. Now if I now fill in the component values, because the R was 1000 divided by 0.25, that will be 4000. So this will give us 4000 S, and plus, if you do this, 1 over 0.25 times 10 to the power minus 6, that's actually the value of the capacitor. You can see that above, then you will have 4 times 10 to the power 6. So this actually is the equation we need to solve. So if you do this, and you might recognize maybe very easily that this is actually the expression for S plus 2000 quantity squared is equal to 0. This means the following, that the solutions S1 and the S2 are both minus 2000. And this will bring us to one of the response types of the second order system, because the second order system can have different responses, like the critically damped, overdamped, underdamped, and undamped. Now the critically damped situation is what we have now. If you have two solutions which coincide, which we have here actually two solutions which are exactly the same, then we have a critically damped response. So this is actually a critically damped response. So critically damped response. Okay, so I will now use the general formula for critically damped response. What is the general formula for critically damped response? The general formula for that is, for natural response, of course. So the general formula for natural response is the A1 times t plus A2, all of them times e to the power minus e to the power s1 t. And that's the general formula if you have a critically damped response. So remember, what we'd like to know is, of course, the A1 and the A2. That's actually the unknown here. And if you fill this equation in the expression for the total response, which is here, then again add the forced response, then we have the complete response. So I will do that also. So I will use that, substitute that. But I will first write down what the S1 is, because that's already given. So we have minus 2000 t. Okay, the next step is the total response. So we have the natural response. Now the following is the total response. So step 4, total response. So let's move on to total response. What is total response? As we said, the VC total is the forced response. Let me write it down again. Plus the natural response. And we already know what the forced response is. That's 1. And what is the natural response? We already have the expression for this, and we will use the initial values to determine the A1 and the A2. Okay, so what are the initial values? Now we already know that the capacitor voltage at 0 is 0, so we can use this. And we know that the capacitor voltage derivative of that evaluated at 0 is also 0. And this is volt per second, and this is volt. So I will need this expression also in my formula, and I will need this expression in my formula. So I have to take the derivative of this, such that I can fill in the 0, and I can set up the equation to calculate the unknown, because I have 2 unknowns, so I also need 2 equations. So let's take the derivative of the expression we have here now. So like this, I will lose 1, and this is a product rule, so I will get A1 times e to the power minus 2000 t, and then plus A1t plus A2 quantity, and then times minus 2000 e to the power minus 2000 t. So if I write it down in a different way, I will have this. Okay, so this is actually the expression for the derivative. And now I will use these 2 conditions and fill in this formula for this part, and I will use 0 here, and I will evaluate it at time equals 0. So what I have is the following. I will start with the first, so I will have for this, I will maybe move this a little bit to the right, so we have some space and we can move underneath it. So I will do it in blue. What do I have is the following. If I fill in 0 here, what do I have? I have the 1. This will be gone, and this will be left, A1, and this will be 1. So I have 1 plus A. So I have 1 plus A2. That will be 0. That means the A2 will be minus 1. So this is actually one of the unknowns. For the second part, I will have this fill in 0, or this. This will be A1. So let me write it down. So we have an A1. This will be gone again. So I have again an A2. And this will be 1. So I have minus 2000 A2. So I will have minus 2000 A2. That will be 0. Now if I now fill in the A2 I already determined here. So what we get is A1 is minus 2000 times minus 1 is equal to 0, and that will give us A1 is minus 2000. So I have actually determined both unknowns, A1 and A2. Thus, what I have is the following. and this is actually the final situation. The capacitor voltage is the following 1, and then I just fill this in. This is actually the complete expression, plus A1 is minus 2000 t minus 1 e to the power minus 2000 t, that is in volts, and it will be of course valid for t larger than 0. And if I just a little bit simplify this to take out the minus sign outside, just extra step, then we'll get the following, which is maybe better for future analysis. So this is actually the situation. This is actually also the final result. So as a summarize, we start with the, I will just zoom out to summarize it. As a summarize, we just start again what we did for the first order transfer response with the initial values. That will give us the situation that we use in the last step. This is actually the same procedure as we did, but the main difference is actually the situation for at time equals 0 plus, which is required to calculate also the situation for the derivative of the capacitor voltage. And if you do that, then you have two conditions which you need to evaluate the capacitor voltage in the final form, because the capacitor voltage really requires a natural response and force response. Now, final value will give you the force response, and we know already how to model the inductor and the capacitor. That's actually also discussed here. The natural response is the situation for the circuit when there's actually no independent voltages or current sources involved, so only the components, what they are doing and what their response are on their own. So it's actually the calculation, and we use again the Kirchhoff current law and the voltage law and Ohm's law where needed, and we require these two formulas. This is really important, so it might be handy for further calculation examples. And we will set up a second order differential equation. We use this operator and we come up with the expression, and we solve this and we determine the roots, and that the position of the roots will determine your response. If this is too distinct, for example, there will be an overdamped response. We will also discuss that in another video, another example. And if this is our complex expression, that will be underdamped, and if it is a pure imaginary, that will be undamped. So we have 4 situations, so I have discussed in this video one of them. Okay, and then depending on the response type, you will develop a general formula for the natural response. It's actually this one. We have 2 unknowns, and we will determine this by substituting this in the total response using the force response in the expression. And you take a derivative because you have also the initial value for the capacitor, also the initial value of the capacitor voltage, the derivative of that. Now, using the procedure we have discussed here, you will get A1 and A2, and you fill this in this formula, and you will get this expression. That is actually the whole story, which is actually not really difficult, but you have to be, again, like in the first order analysis, follow the steps step by step, and redraw the circuit when needed if you have difficulty to see the situation for the specific circuit. So that was for the first example. I will continue with the second example to clarify also the other responses for the second order circuits. So keep in touch, and I'll see you next time, and good luck and take care.